What's going on, everybody? Mr. Diamond. We are here in, I guess, numerically it says chapter 5, but it's actually chapter 4 of senior physics. We're going to be going over work, power, and energy. There's probably more specific ways you could do this title, but really these three things are what we're going to focus on. And in chapter 1, or section 1, we're going to look at work and power and energy. They're all really like pent up concepts together. Power we're going to talk about, but then we're not really going to use until the very end for reasons that will probably make logical sense by the time we get there. We're going to do like one example problem about it, and then the last worksheet of this chapter will be power, and that will also kind of serve as a good review for all the stuff because it'll pull in all of the concepts we talked about. So if you look around for energy online, you're eventually going to run into like a bunch of physics teachers and like crash course places and Khan Academy and like blogs from random other people talking about how weird of a concept it is. Before we continue, I want to mention one thing that like I joke about sometimes in class, but like we really do need to remember is the truth. And that's that most of physics and most of science in general is us assigning values to things to better our understanding. When we've decided what a meter is, that's like a thing we've arbitrarily chosen. If you look up what the definition of a meter is in the SI units, it's like some absurd, like random calculation of a number from some natural source. Like there's a whole bunch of very just bizarre measurements that we've selected. And we've selected them because they're convenient, because they're good for our size. Like if we were like mice, meters would be huge, kilograms would be gigantic. If we were whales, we would need something that's like a bigger, smaller size. So we've picked something arbitrarily that's convenient for us as human beings, and we're trying to understand something that's happening in the universe that we're just putting numbers to it. We're taking our inability to comprehend something and trying to comprehend it by putting it into numbers. So energy is not a thing that exists. Like energy isn't a thing that was created at the beginning of the universe and then like we somehow discovered that concept existed. We just have defined energy as a term that comes to mean something about the world around us. It's something that we use to describe things that exist in nature, but energy, quote unquote, does not exist. It's a description of something. Like if you say that has energy, you're not saying something like, oh, it's blue or it's red or it's green. I mean, I guess if you're talking about like the vibe that it gives off, but like when you say like this like bullet has a higher energy than this ball being thrown, you're not saying that the bullet has actual a thing, matter that's different. It has a idea, something that's about it that's different. So even with that knowledge, energy is one of the most foundational and important concepts in all of science, and it still is really confusing. Between chemical reactions, charging your phone, lifting a box, heating popcorn, all of these things involve what we would define as energy. We could all agree they involve energy being exchanged or going from one thing to another, or they have energy, but pinning down what that means is a problem. Because if you start saying like, well, the bullet example I used, well, that was like energy because it was traveling fast, but like a block of uranium has energy. So, well, that's chemical energy. Well, there's also electrical energy coming from like charging of the phone. So pinning down like one exact definition is hard because you can describe a lot of instances where they exist, but actually like figuring out what you mean can be a problem. So the roots of the word actually gives us a good definition. The first recorded use was like 350 BCE, where the word energia was used. It's probably a horrible pronunciation. It might be energia. I don't know. I'm pretty sure it's energia. But in that context, it was translated as activity or being at work. The literal translation meant to contain work. In meaning inside and ergia meaning work. So by that definition, and putting that through a modern lens, we get the definition that energy is the ability to do work. For the foundational concept of all of science, that's not very helpful. We would agree that like a bullet can do work, and electricity can do work, and uranium can do work, but like now we have to ask what is work, and energy itself is not really super clear at this point. So we could be a jerk here and just say, well, that means that work is the process that exchanges energy, but that doesn't seem like very helpful. It's kind of a cop-out. So let's look at an example to try to actually explain what's happening. And the way that we're going to do that is we're going to jump the gun here because explaining it is just so difficult. There's two equations we use to describe work, and it's whether you come at it from a calculus or an algebra standpoint. We're going to stick with the algebraic version over here, but if you like calculus, you can think of it in this term. It's basically going to be the same thing. Work is equal to the force times the change of displacement, or how far it moves, times cosine theta, which is theta in this case is the angle between the force and the displacement. So if the force is going this direction and the displacement is going this direction, it's the angle between you're pushing this way, the thing is actually moving this way. And we'll talk about that in a lot more detail in class. We're going to focus on the non-calculus version. So really we're caring about two major things. What were the forces acting on the object in question, and how far did the object move during that time, during the time that force was acting on it. Notice they don't have a direction related to them other than for theta. That's because work is a scalar quantity, and therefore energy is also a scalar quantity. Again, you're not saying like it's traveling at this speed, so it's going this direction over this period of time. It's just an amount of ability to do something that it has. And we wouldn't say that it's like, oh yes, it has to the 5 degrees to the north amount of work. Like, no, you did work, or you had used energy. There wasn't a direction associated with it. It's not like if I push this way, I pull energy that direction, and then if I do this, I just get all that energy back. It doesn't work that way. So these have to be scalar quantities. So we're going to do an example of this. Let's think of a rocket ship that's floating motionless in space. And we'll say that the engine exerts 10,000 newtons of force, so it's coming out of the end of this rocket going this way. And it's going to go over 60 seconds. It's going to cause this 2,000 kilogram rocket to go 100 meters. The energy of the engine has then acted upon the rocket. In this case, the gases leaving that way are going to cause an equal and opposite reaction, thanks to Newton's laws, pushing the rocket itself forward, and it's going to make it travel 100 meters down the line. So how much work was done? According to our work equation, work equals the force times the displacement times cosine of theta. The force exerted was 10,000 newtons, because we were given that in the problem. The displacement was 100 meters. And then for theta, we ask ourselves, how did the rocket move and how did the force apply itself? We know that the gas moved backwards, but that gas leaving is what propelled the rocket to the right, or this direction in our picture. And so it's moving to the right, and our engine is going to the right. So they're going the same direction. They are parallel to each other. That means the angle between them would be 0. There's no angle between the force and between the movement that it has undergone. So we'd end up with 10,000 times 100 times cosine of 0. And if you have not realized, or if you don't remember, cosine of 0 will equal 0. It means that equal 1, sorry, not 0, otherwise this whole thing would just go away. It equals 1, and so you don't actually have to worry about it affecting it. If they're going the same direction, you don't need to account for it. Cosine of theta is really just there for if you're pushing on it, you're trying to figure out what force is going the same direction as the movement that the thing is traveling in, and you're trying to figure out what component of it is actually going the direction you care about. That's the whole goal of the cosine here. So plugging this in, you get 1 million, which is 1 times 10 to the 6th, and then unit-wise, we would get newtons times meters, which we define as a joules. It's how many newtons per meter that is being traveled, or times meters being traveled. Another commonly non-SI unit used for work, and therefore energy, because they're tied together, the same unit for work as the unit for energy, is calorie with a lowercase c. 1 lowercase c calorie is 4.184 joules. Americans are hilarious and love being tricky, so the calories that are listed on our food have capital C's. That's not for like English reasons. Capital C actually is the same thing as a kilocalorie, which means 1 kilocalorie is actually 4,184 joules. So if you ate something that has 100 calories, you've got like 4 million joules worth of energy inside of that thing. So there's like a whole lot. It's really, really big, but it's because if they listed the other numbers, everyone would probably feel really bad about the food that they ate. So while we're in class, we're going to do a whole bunch of examples determining the angle between forces and the work done, because that's one of the most important pieces of this, and because it could show you some really interesting and some strange conclusions about work and the force that you're applying on something. This last piece is going to be more relevant later on, but while we're here, I mentioned that the unit joules can go for both work and for energy. I was joking about how, oh, well, work is the process of exchanging energy. Haha, look, I just answered the question with or gave an answer based on the question. But like that actually is true. It really is. Work can also be defined as a process of exchanging energy. And so that actually has a specific name that we can actually use, which is called the work energy theorem. And that is that the net work done on an object will be equal to the change in kinetic energy of that object. So if I know that I worked and I put this much work into that rocket, I also therefore know how much kinetic energy or how much energy that object has. So we would say that it was work W net work equals the change delta KE, kinetic energy. But we're going to talk about kinetic energy in a little bit, so don't freak out about that. I believe that is the last piece of this slide. We're going to do a small separate video over power that we'll get through. It's not going to be too much to worry about. Like I said, we'll come back to that a little bit later, but it's a convenient time to define it. In the meantime, though, this has been Mr. Diamond. If you have any questions, please let me know. We'll go over a bunch of this stuff in class and draw some pictures and do some other work. I hope you have a great rest of your day, everybody. It's Mr. Diamond signing off.